This week, we're going to finish the second half of Lecture 7, which is about image enhancement. And I will start this week's content with spatial enhancement. And before introducing different methods for spatial enhancement, I would like to introduce a concept first. It's called spatial frequency. So it refers to the number of changes in brightness value per unit distance for any particular part of an image. Spatial frequency in remotely sensed imagery may be enhanced or subdued using two different approaches, spatial convolution filtering or Fourier analysis. So now on the right side of this slide, we have four figures. From left to right, from top to bottom, we have figure 1, figure 2, figure 3, and figure 4. So there are strips in all of them, for sure. But for some of them, there are more strips than the rest. Okay? According to this definition, spatial frequency is decided by the number of changes in brightness value per unit distance. So by this definition, when you compare these four images, which one has the lowest spatial frequency? Which one has the highest spatial frequency? Okay, you can pause here to observe them and to make your judgment. Okay, but now I can give you the answer. The top left one has the lowest spatial frequency, and the bottom right one has the highest spatial frequency. Because obviously, in these four images, they're all addressed by different grayscales, right? But the first image has the least strips, while the last image here has the most strips. And if we make these four images simpler, we say there are two land cover types. Land cover type 1 is addressed by white pixels. Land cover 2 is addressed by black pixels. And of course, there are gray pixels. Okay, we can consider gray pixels as the boundary between two land cover types, white pixels and black pixels. Be careful. I'm making this simple. I'm making this description simplified. So we consider there are only two possible land cover types, black and white. But when you're actually dealing a remote sensing image, all those grayscales, they could be other land cover types. Okay, so I'm just trying to simplify the problem here. Okay, let's just assume we have two land cover types, black and white. And the rest pixels, they're in different grayscales, other grayscales other than white and black. We consider them all boundaries. Okay, so the number of changes in brightness value per unit distance. Okay, so this picture, this image has the lowest spatial frequency, while the bottom right one has the highest spatial frequency. In other words, in this first image, we see less change between white and black when we compare this image to the bottom right one. In the bottom right image here, obviously we have more strips. You can consider black as strips or white pixels as strips, doesn't matter. Which means that, okay, the change here is more frequent. The change of what? The change between black and white, between land cover type 1 and land cover type 2. Okay, so this is called spatial frequency. And because we're talking about remote sensing imagery, which means that each pixel in each image, in each remotely sensed image, has a location in the real world, or at least has a relative location in that image, right? With a column number and row number. So there is this spatial context applied to these images because we're talking about these images in remote sensing class. But you should know that this concept of frequency is not exclusive to remote sensing. Actually, in image processing, which is a branch of computer science. In telecommunication, the concept of frequency here has been widely used. Okay, the number of changes, not in brightness value. Maybe in remote sensing, in image processing, this concept of brightness value is still usable. But in telecommunication, maybe in unit time instead of per unit distance. Okay, and it changes not only in brightness value, maybe in 0 and 1. Okay, in a binary format of data change. Okay, per unit distance, sure. Per second, sure. Per microsecond, sure. So this concept of frequency can be widely used in other disciplines. You should know that, okay? But in remote sensing, when we're looking at these images, we give a spatial context to the concept of frequency. We call it spatial frequency, and it is the number of changes in brightness values. Okay, not in other form, per unit distance, not per second or per hour, per unit distance. Because when we are having this spatial context, distance is important. Okay, so spatial convolution filtering, if we delete the spatial part, convolution filtering can be widely used in other disciplines, like I mentioned. Spatial convolution filtering are based primarily on the use of convolution masks. Okay, I'm going to tell you how to do that. And Fourier analysis, which mathematically separates an image into its spatial frequency components. The second one is more complex, and in this entering level remote sensing class, we're going to talk about more about spatial convolution filtering. Okay, here we go. So spatial convolution filtering, it uses a linear spatial filter. Okay, here is a concept. What is a filter? What is a filter? I'll tell you later. For which the brightness value, of course, it can be addressed by BV ij out. Ij is for column number and row number. Out is the output value of a pixel after this filtering process. A location ij in the output image, right? BV ij out is a function of some weighted average or some weighted linear combination of brightness values located not everywhere, located in a particular spatial pattern, or we say located in a neighborhood. Okay, neighborhood can also be considered as a mask. So spatial pattern, neighborhood, mask. When we're talking about them, they are the same. Okay, under the concept of spatial convolution around the ij location in the output image. So in other words, it means that when we're using when we're applying a spatial convolution filtering process to an image, each pixel's value will be recalculated based on its neighborhood or based on its neighboring pixels. Okay. So here is a very simple illustration of spatial convolution filtering. So at the bottom, we have this image, right? At the bottom layer, we have this image with pixels. Each square here is a pixel, okay? And there is another layer here. It's a 3x3 square window. This is the linear spatial filter. It can be called as a filter. It can be called as a neighborhood. It can be called as a mask. No matter what, it's a 3x3 window. Okay. Of course, you can assign other shapes to this window, but that's another story. I will tell you later. But here, let's just say this is a simplest situation. We have a 3x3 window, and because this is a 3x3 window, there is always a central pixel right here, and that central pixel is the one we want to assign a new value to, and that new value is based on all 9 pixels within this window. Okay, and this window will stop here, or you can say this window will always start from the bottom left corner of your image and recalculate a specific value and assign it to the central pixel. And this window will move to the right by 1 pixel and repeat this process to change the value of next pixel. And you can imagine this window will go through all pixels within this image. And after that, obviously, values of all pixels in this image will be changed, and all pixels will have new values. Okay, so this is a very simple, straightforward spatial convolution filtering process. You open a window, apply that window to a pixel in your image, and recalculate. Or you can say simply calculate a new value for that central pixel, assign that value to the central pixel, and you go to next pixel. And you repeat until all pixels in this image have been what? Have been dealt with. Okay? So if coefficients, say I, in the mask are multiplied by the following individual brightness values in the input image. So we have 9 pixels, right? So pixel 1, pixel 2, pixel 3, 4, 5, 6, 7, 8, 9. When a window is applied to this neighborhood, say 5, or let's just say pixel 5 is the central pixel, right? So like I said, you need to calculate a new value for the central pixel using all pixels within this window. And you can assign weights to different pixels. A weight can be considered as a coefficient for a specific pixel's brightness value. For example, we can assign C1 as the weight of the value of pixel 1, which is addressed by BY1. So C1 can be any number, right? It could be 0. If it is 0, it means that, okay, there is no weight for pixel 1, which means pixel 1 does not work, does not affect the calculated new value for the central pixel at all because its weight is 0. Of course, you can change C1 to 1, which means that, okay, a BY1, which is a pixel value of pixel, which is the brightness value of pixel 1, will be simply added to your new calculated value for central pixel. So C1 can be a 0, can be 1, can be 0.5, can be 0.9. Actually, you have to assign a specific weight for each pixel within this window. So we have C1, C2, C3, until C9. Okay, and when you assign different values to these coefficients, the function or the performance of your mask, of your filter will change accordingly. Okay, scientists, researchers, they have been working hard to create different types of masks to implement different enhancements on remote sensing images. So of course, you can use different shapes for windows. And more importantly, you have to assign coefficients carefully. And again, there is no so-called correct coefficient or wrong coefficient in this context. It all depends on your application. No one is asking you to use a specific set of coefficients for a specific image. Okay. So there are types of spatial filtering. They are all based on this frame. What frame? This window filtering frame. Okay, no matter what kind of spatial filtering you're going to use, this is a framework here. You open a window, you open a mask, and you use different coefficients to assign different weights to different pixels within this window, within this neighborhood, and eventually you calculate a new value for the central pixel. Okay, so when we're talking about different types of spatial filtering, we have low frequency filtering, we have high frequency filtering, we have edge enhancement filterings. Okay, let me show you how they work. But before that, like I said, you can define different shapes for your masks or for your windows, for your neighbors. They're the same, like I said. Here are some examples. Okay, we call them masks, or we call them kernels, we call them neighborhoods. They are the same thing. Okay, and this is the simplest window here, right? I showed you here in this illustration, right? So it's a 3x3 window. We can make it 5x5, 7x7, 9x9, but this pixel number here must be an odd number, 3x3, 5x5, 7x7. Why can't we use 4x4? If it was 4x4, then there is no central pixel, right? If there is no central pixel and you finish the calculation based on your 4x4 filter, say that, who should you assign this new value to? You don't have a central pixel, okay? So that's the first thing you need to know. No matter what kind of mask you're trying to use, make sure there is a central pixel to assign the new pixel value to, okay? Okay, so low frequency filter to surprise high frequency detail. Okay, now you need to be careful with this concept, okay? This is low frequency image with less boundaries, right? But here is a high frequency image. There are a lot of changes within each unit distance. There are a lot of boundaries between land cover type 1 and land cover type 2. Okay, since low frequency filter is here to surprise high frequency detail, so you can imagine that the purpose of this low frequency filter is to smooth the boundary or smooth boundaries among different land cover types. Okay, so what is smooth? What does it mean? What should I expect? Later you will say that. I will provide example. But here, let's say this is a window for low frequency filter. It's a very typical simple 3x3 window. And you can say the coefficient stays the same for all 9 pixels, which is 1/9. So what's the result of this? This is a mathematical mean. Or you can say this filter is trying to find out the mathematical mean of 9 pixels and assign that mean value to the central pixel. It's just that easy, right? So on the right side, we have this mathematical equation here, and eventually this int means integer, because eventually when you calculate the mathematical mean of 9 pixels here, you could have an integer that's convenient. You just take it and assign that value to the central pixel. If the result, most likely, it is not going to be an integer. If it is a decimal, you just need to find out the closest integer, or round up, round down. It depends, but eventually you will have an integer value for the central pixel. But be careful, it doesn't mean that all remote sensing, all pixels in remote sensing imagery have values of integers. Okay, it means that the value of a pixel could be a decimal. For brightness value, it should be integer. But if it is for reflectance, for temperature, okay, it could be decimal. But here, let's just say we're talking about brightness value, so eventually it should be an integer. So here, if you look at this equation carefully, it's just add the pixel and brightness values up and divide that result by 9. So that's actually the mean value, right? And that mean value is the new value for the central pixel. Okay, so for example, so here is a window, right? Here is a window indicated by gray squares. So 3x3 window right here. Okay, so if you add all those pixel values up, it should be 27, and divide that value by 9, which is 3. Okay, so 3 will be the new value for the central pixel. Which is the central pixel? This is central pixel. It used to be having a value of 5, but after the filtering, it is 3. And then you can move this window to the right by 1 pixel, and now this pixel with the value of 4 should be the new central pixel, and you need to calculate the average value covered by this filter again, but this filter has moved to the right by 1 pixel, and you should have a new value. Conveniently, it's 4 again, but it's just a coincidence, right? And you can do this repeatedly for the next pixel and etc. and etc. After the first row of filtering, you came back to the very left of the pixel and do the next row. Okay. So example here on the left side, we have original contrast stretched image here is true color. We have a building here, should be a house because there is a parking lot. There is only 1 car here. Okay, so this is a house roof, right? Asphalt or concrete for parking lot. Okay, and here is a road, obviously it's concrete or asphalt. And this house, this family is surrounded by a shrub, or you could say bush, right? And then we have grass, and here is a light pole, because you can say here is the shadow, a linear shadow, which means that sun is somewhere on this direction, right? Because the shadow is on the other side of, should be on the other side of the light pole when we're talking about sun's position. So it's a very simple image with very typical land cover types, right? Roof could be a lot of materials, plastic, metal, even asphalt, right? And we have concrete or asphalt, which is very common for constructions. We have vegetation, different types of vegetation. On the left side, we have a tree canopy here. It's part of a tree canopy. And we have grass, okay? We have evergreen. I think it's evergreen bush, because this tree here looks not very green, so it should be autumn or winter, but it's a very simple image with almost all typical land cover types. Okay, see that? So on the right side here is the image after the low frequency filter. Okay, so what's the difference if you compare the left one and the right one? Obviously, the first difference is that on the right one, we are using grayscales instead of real colors to address the whole image. That actually does not matter to filters. But when we're looking on the right side, it's not that clear anymore. When we're talking about clear, we actually means that this image is not that sharp anymore. And you can see the boundaries between land cover types. For example, the boundaries between this parking lot and this car is not that clear enough if you compare this image to the image on the left side. And you can say all those twigs, or all those branches are within this tree canopies. Their boundaries on the left side is relatively clear, but that same canopy in the right image, all those branches of trees or twigs, they're not clear. Their boundaries are not clear anymore. So, like I said, low frequency filter is to suppress high frequency detail, and high frequency detail usually refers to boundaries between different land cover types in remote sensing imagery. So you can say here is the result. You should have a first impression of this result of low frequency filter. It makes your image less sharp. Boundaries are smoothed. By what? By this very simple average filter. Okay, so this is the result. So since we have low frequency filter, right, we also have high frequency filter. to suppress low frequency detail. So if low frequency filter was there to smooth the image, then you can guess high frequency filter, what's the purpose of it? To make boundaries sharper, right? It's the absolute opposite of what the low frequency filter did to that image. So I will show you examples later, but here is the equation, right? So a high frequency filter for edge enhancement or boundary enhancement. Okay, so here is the filter. Okay, and this is the result. It's the same image. After high frequency filter, you can see those boundaries between land cover types. They are very clear here. Okay, so here is just another example. So output, or you can say this is actually a transformation from low frequency filter to high frequency filter. Okay, if we are using this 3x3 window, so which is pixel 5? Pixel 5 is the central pixel. It means that if you have done the low frequency filter, or if you have done low frequency filtering to the whole image, to a whole remote sensing image, right? And the output for each pixel can be addressed by this LFF5. It is 5 because it's the central pixel. Out, because it's LFFF, it means that it's low frequency filter. You can multiply each pixel's value by 2 original value. Okay, and use that result to subtract the output of low frequency filter. Okay, of course, the value after the low frequency filter for the same pixel, and the result is high frequency filter. Okay, so this equation here is for you to convert from the output of low frequency filter to high frequency filter. But if you didn't do LFF, you just want to do HFF directly, you are just using, you're going to use this very simple mask here. Okay, so high frequency sharp edge filter applied to the red band. Okay, so of course, this image is a combination of 3 bands from remote sensing data, from satellite data, right? And specifically, red band is assigned red in this image. A green band is assigned green in this image. A blue band is assigned blue for this image. And if we only do HFF for the red band, this is the result. Okay. And on the other hand, if we do LFF to the red band, again, this is the result. So after LFF, the image is becoming blurry, okay, especially boundaries. But after after HFF, high frequency filter, all those boundaries, they're becoming sharper than before. Okay, so this is the difference. And I'm going to give you more templates for edge enhancement. Some of them, they are called embossing. Okay, embossing east, this is the template. So basically, only 2 pixels are joining this filtering. The pixel on the left side of the central pixel and the pixel on the right side of the pixel. You can say if the left pixel is larger than the right pixel, you will have a positive new value for the central pixel, because 1 multiply left one minus 1 multiply the right one. But on the other hand, if the pixel on the left has a lower bright value than the pixel on the right side, what is going to happen? You will have a negative value because you are going to use a smaller value to subtract a larger value. what is going to happen? You will have a negative result. And negative result has no meaning. Negative brightness value has no meaning. It's meaningless to remote sensing image. So eventually, your new central pixel will have a value of 0, which means that that pixel will be totally black. Okay, so that is this emboss east mask template is trying to do. It is actually comparing the left pixel and the right pixel of the central pixel. So emboss northwest is actually doing the similar thing, but it is actually comparing the pixel to the north east of the central pixel and the pixel to the southwest of the central pixel. Similarly, like I said, different scientists, researchers, they have created different mask templates for us to use daily in our daily research, in our daily work. Okay, some of them are listed here. Another type is called campus gradient. So you can say it's just different coefficients are assigned to different pixels within this 3x3 window. Okay. So I'm going to provide some more examples. Here is the emboss northwest filter result. Of course, based on that image we saw before. You can see here the feeling of texture here is actually stronger than before, right? You can see that this is almost a 3D version of the original image, because we can see that the grass, we can say there are wrinkles for grass, for canopy, and also for this roof of the house, right? And you can say there are dents on this road, and they are not actually real dents, not necessarily real dents or real small holes on the road. This 3D impression you have was created by this emboss northwest filter, and this filter is not based on the actual elevation of each pixel. It's based on each pixel's brightness value. So this seemingly 3D effect here is not actually based on the different elevation values of all those pixels. It's based on their values, brightness values. Okay, so don't get fooled by this image. It's not a real 3D image based on elevation. Okay, it's based on brightness value. Okay, and also we saw this picture before. It's the picture for Savannah River and 4 Miles Creek, right? I mentioned that someone is charging something into this 4 Miles River, 4 Mile Creek. It makes it very hot, relatively hotter than the Savannah River. And this is the image after campus northeast filter. Okay, so some examples here. And like I said, when you're working with a specific remote sensing image, you want to enhance some part of the image to retrieve more information, right? Like I said, there is no so-called correct answer or wrong answers for the choosing of filtering methods. Okay, it all depends on your application, your specific work. As long as you can retrieve more information, as long as you can retrieve what you want from the image, then it's a good one for you. It's working, right? So under a lot of scenarios, we just try a lot of them. We try different templates. Because eventually your software is going to do all the calculation, and spatial convolution filtering is not computationally it's not very, say, it does not consume a lot of computational resources, let's say that. So in other words, it will be pretty fast for computers nowadays to finish this filtering process. So just try them, okay, and see which one is proper. Okay, Okay, that's all I want to say. In this video, I'm planning to use another one long video or two shorter videos to finish the second half of lecture 7. Okay, I will stop here and I will see you in the next video. Thank you.